Let me get one thing straight right from the start. I'm just sort of a messenger. As Upender says, it comes from the President and Congress to Charlie Bolden, and then goes down to the people in the Earth Science Division in the academic community and in our NASA centers who actually get the job done. Somewhere in between there, it comes across my desk and hopefully doesn't get lost. So what I was asked to do today, and what I will do today, is to talk to you about our program from a somewhat NASA-centric standpoint, our Earth observation program. But of course, as you heard this morning, and as you well know, no single agency, no single country can do everything that is necessary. So talking about the NASA program perforce involves talking about international collaborations. Also, for this particular group, I don't have to spend a whole lot of time, like I do for some other groups, explaining why it is that NASA, the space agency, or any of our space agencies observe the Earth. It's quite clear. We live on a planet that is incredibly complex. As Jean-Yves said earlier on, the vantage point of space is not only unique, but it's essential, and we'll talk a little bit more about that. The system engineering skills that we as space agency people apply to many different problems are particularly effective in looking at understanding the Earth as a complex system. And finally, we do hard things that are important and that are influential, and never forget the fact that since we are looking at the planet where all of the people live, and oh, by the way, all of the voters as well, we have the opportunity to improve the lives of all humanity with what we all do. So, as Jean-Yves said, the spaceborne perspective is absolutely key to understand the Earth as an integrated system. Not only the individual processes, but the connections between the processes. We have got to make measurements of many different variables on many different scales, because everything is linked. And the ability from the vantage point of space to be making measurements of many different quantities with near global extent, but with high spatial resolution over long periods of time, but with frequent revisits at any place, is a unique aspect of our spaceborne instrumentation. And that is why, indeed, we as space agency people are leading the path to understanding Earth system science. And what's shown on this chart is actually both the present NASA research satellite fleet, which is on the lower half of the chart with mission names that are sort of in blue and green. And we're flying about 20 missions and major instruments on other people's missions right now. And on the upper portion of the chart are only those missions which are well along in development for launch between 2016 and 2022 or 2023. So we have about 20 missions that are flying now, and a nearly equal amount that will be launched by NASA for our research satellite fleet over the next 5, 6, or 7 years. And you can see from the red squares that international hardware collaboration on the missions is more the rule than the exception. This chart just simply shows for our present on-orbit fleet of NASA research satellites, not the coverage, but the orbit tracks that they are taking. You can see that there are many, many different missions. Each one of them sometimes is measuring several quantities themselves. You can see the ISS, where we have several instruments, as Charlie Bolden mentioned, flying in its inclined orbit. we have many spacecraft that are flying in sun-synchronous polar orbits, including, you can see it going up on the right-hand side, the A-Train Constellation. In fact, between NASA and our international partners, we have for many years been constructing essentially a virtual observatory by flying multiple spacecraft in relatively close physical formation or constellation and exchanging the data from all of the different instruments and all of the different missions. We can take measurements that are near simultaneous at a point and the capability of the constellation is larger than the possible capability that we could ever have by trying to hang all of these instruments on a single spacecraft. You can see by looking at the microwave limb sensor on Aura all the way on the left of the screen. It actually has a viewing geometry that's looking ahead, and it's making measurements that are simultaneous with the measurements from Calypso and near simultaneous from CloudSat. So we're flying research satellites in formation in low Earth orbit, and we're also making measurements from L1, the Lagrange 1 point, 1.5 million kilometers from Earth. This is a point that is more or less on the Earth-Sun line, so you're always looking back at the Earth and seeing the entire sunlit hemisphere at once. And we have two Earth science missions on Discover. It's a joint NOAA-NASA mission. Its primary use is to make measurements of space weather 1.5 million kilometers up from Earth. But you can also see that when you're that far away from Earth, you're actually outside the orbit of the Moon. And so periodically, the Moon transits across the face of the Earth, and this is from our EPIC camera on Discover, showing a lunar transit. We know exactly when they're going to happen. The Romans probably knew when they would happen. Actually, the face of the Moon that's shown there is from Earth, the so-called dark side of the Moon. That's the face of the Moon that faces the Sun. You go figure. But we don't only take pretty pictures of the entire sunlit hemisphere of the Earth, but the EPIC camera, which makes measurements in 10 different spectral bands, also makes near simultaneous measurements over the entire sunlit hemisphere of things like stratospheric ozone. And this is a comparison on the right of an EPIC, almost instantaneous view of hemispheric stratospheric ozone. And on the left, a rather laboriously constructed over the better part of a day set of measurements from the OMPS, the Ozone Measurement and Profiling Suite, NATOR instrument on the SUMI NPP mission. And you can see that even early in the Discover mission, the two sets of measurements are extremely similar. And this gets me to an important point that was touched on by Dr. Jimenez earlier on, which is the CFC and ozone problem. This is an example where the nations of the world got together, implemented a policy to change our species business practices, if you will, to attempt to eliminate chlorofluorocarbons that were destroying the ozone level. And our spaceborne observations allow us to track the efficacy of the policy that was put in place. And you can see the model here in the solid dark line suggested that right around this time, that the ozone concentrations would continue to decrease, that is, the size of the ozone hole would increase over time until right about now. And over the next several years, we should see a rapidly increasing rate of decrease in the size of the ozone hole, or an increase in the total stratospheric ozone, so that by the 2070 time frame or so, ozone levels should probably be back to where they were for our grandchildren at the time that some of us who are rather ancient here were growing up. So this is an example of spaceborne observations and monitoring of policy decisions. We're also making measurements, as we heard earlier, of atmospheric carbon dioxide mixing ratios, total CO2 levels. These measurements can be used into the future for not only understanding the Earth system and the roles of large distributed sources and sinks such as the boreal forest and the Southern Ocean, but also to measure the efficacy and track the efficacy of policy decisions that are made. This is an example over a couple of months during last summer of the Earth breathing, as you will. In the upper left-hand corner, you see Orbiting Carbon Observatory 2 measurements from late May of 2015, and carbon dioxide levels are high in the northern hemisphere. It's just at the beginning of spring. There's been a lot of emission in the northern hemisphere, but as time goes on, as you see in these various 2-weekly or 16-day images, you see that in fact the vegetation, the terrestrial vegetation, has greened up and is fixing carbon dioxide from the atmosphere, transferring it to the land, and atmospheric carbon dioxide levels are indeed decreasing. Here's another example of monitoring the Earth from space over long periods of time and large spatial extents. This is the result of an analysis that uses the last 13 years or so of the more than 40-year Landsat 30-meter multispectral data set, the longest set of consistent spaceborne accurate observations that we as a species have collected. And the interesting thing I find is to look in the lower right-hand corner, which is chart D. So these are global changes in land cover and forests in particular at 30-meter resolution over the entire globe for 13 years or so. And what you can see in the lower right in the colors are basically forest loss and forest gain, and the purple in the middle are regions where there was both loss and gain over this more than decadal time frame. And if you look at the southeastern portion, for instance, of the United States, you see that, in fact, that's a huge region of both lots of forest loss and lots of forest gain. This is a measure of the fact that these are managed forests, and the owners are cutting down the trees for their carbon and for their wood products on about a 50-year cycle. So every year, 2% or so of the forests get cut down, they get replanted, so there is continual change there. These are the sorts of observations that we can make from the vantage point of space of important climate and societal impact variables. I'd like to spend just a little bit of time here talking about the situation that we have right now, where from our spaceborne measurements, we are measuring virtually all of the reservoirs and all of the fluxes in the hydrologic cycle, in the water cycle of our planet. And we've seen allusions to many of these observations in previous talks from my colleagues and the heads of agencies earlier in the day. We know with accuracy and precision that on a global mean sense, sea level is increasing by 3.2 millimeters per year plus or minus about 0.4 millimeters per year. We know this from the precision altimeter satellites that first NASA had CNES, and then NASA, NOAA, CNES, and EUMETSAT, and soon those parties and the EU and ESA will be making into the future. So sea level is rising at 3.2 millimeters per year in a global average sense, but we're also making measurements with the GRACE gravity mission of the changes in mass in the ocean, and that's what the green line shows here. And you can see that the equivalent sea level rise of the mass changes in the ocean only account for about 1.8 millimeters per year of that rise. So we're melting water that was on ice sheets and glaciers inland and adding it to the ocean. But the sea level rise globally in the ocean is considerably larger than the amount of water that we're adding to it. And of course, the basic answer there is that the upper ocean is warming as well, causing a thermal expansion, a change in density, but not a change in mass. So by making these multiple measurements of different quantities and analyzing them together, we not only see what is happening, but we see why it's happening. We're making measurements from microwave instruments on orbit of sea ice extent and sea ice thickness in the Arctic, for instance. And what's shown on this plot in the dark black line on the plot is the time series of basic decrease in the extent of maximum sea ice in the Arctic. But in each one of the thumbnails, you can see in the colors the fraction of multi-year ice. Red colors correspond to thick ice that has been formed and that has been present for many, many years. And even more than the decrease in ice extent, you can see that over time, our satellite measurements are showing us that the fraction of thick ice is decreasing far faster. And the interesting part about this is that the modulation of thick ice has to do with basically ocean temperatures. But the modulation of thin ice, first-year ice, has to do with solar insolation, that is, cloudiness. The change in controlling effects from ocean effects to atmospheric effects, if you will, are the sorts of things that can potentially cause tipping points and rapid climate change. The GRACE gravity mission not only measures changes in gravity, which can be interpreted as changes in mass of water in the ocean, but it can also look subsurface, and it can see the changes in aquifer levels indirectly by measuring the mass changes under the surface where the aquifers exist. And we have a long time series of global measurements of water in aquifers, and you can specifically see here in on the northern subcontinent here and into Pakistan, both the annual changes in aquifer levels as measured by precision gravity from satellites and overall the long-term changes. In general, we are pumping water from aquifers that have taken thousands of years in some cases to basically fill, and we're pumping the water out of them on time scales of a few decades. That water is being used for people to drink, to irrigate fields, for agriculture, etc., but it is unsustainable. And you can see here the global view over a decade or so of major aquifers around the world, and you can certainly see in the northern subcontinent, you can see in the Central Valley of California, and many other regions where we are draining. Those are the pink and red regions where we're draining aquifers unsustainably. We heard about the global precipitation measurement Constellation which is built around the core satellite that was GPM, that was launched by JAXA and NASA a couple of years ago. But measurements of precipitation from many different instruments on different international and interagency satellites are being used to, for the first time, make accurate measurements of precipitation globally over the world. We are also flying a mission called the Soil Moisture Active Passive mission. It's now passive because the active instrument failed, but it is continuing to make measurements of global soil moisture and of sea surface salinity. So what's shown here are both on the bottom global precipitation from GPM, and on the top soil moisture and sea surface salinity from the SMAP mission. And if you take the time, you can find areas where it rains hard over land, say over Amazonia, and the soil moisture goes up, the rivers start to run. You can see that the Amazon increased flow leads to low surface salinities, et cetera, et cetera. I mean, it's not an amazing observation that when the rains fall, the soil moisture goes up, and when the rains fall over the ocean, the sea surface salinity goes down. Nonetheless, we are quantifying this routinely from the satellites over time. These measurements are being used operationally in the US and elsewhere to drive drought models and monitors to provide direct information that's tailored for the agriculture and management sectors. And globally, we are using measurements of vegetation indices, soil moisture, and others, and evapotranspiration from our spaceborne instruments and missions in order to judge the health of crops globally. And this is being done on an independent UN-based basis, allowing visibility for everybody into the global state of all of the major grain crops for humanity. This level of transparency aids food security because it is frankly no longer possible for one sector to attempt to corner the market in a particular grain like wheat, as happened in the early 1970s, driving up prices and changing availability globally because the information is available to everybody. We've heard earlier that measurements from spaceborne assets, such as JAXA's LOS-2 L-band synthetic aperture radar, here processed using NASA algorithms to indicate damage proxy, so our satellite measurements are being used to help guide disaster response in nearly inaccessible regions. Here the example of the disaster, of course, was last year's Kathmandu, Nepal earthquake. And finally, making measurements globally of many different variables, combining the measurements from different missions, from different nations' spacecraft, really allows us to understand not only what is going on in the Earth system, but why it's going on. We talked earlier about the fact that pretty much inexorably sea level globally is increasing by about 3.2 millimeters per year, as you can see in the upper right. However, in 2010, 2011, where I have it circled, you can see that sea level actually fell in that 1 year by about 5 millimeters, far more than a typical year's increase, and it's in the other direction. What happened? We know that the sea level globally fell from the altimeter satellites. We know that during that time we switched from an El Nino condition to a La Nina condition, so surface temperatures over much of the tropical oceans decreased, the oceans contracted, and so sea level decreased even more. But that only accounts for about 40% of the sea level drop. In fact, by making measurements from the Tropical Rainfall Measurement Mission and others of precipitation, we see that there was increased precipitation over the Indonesian area, especially there was increased precipitation over northern South America and in Australia. And in fact, we have closed the hydrologic budget, the water budget during that time. If you look and see how much more water was put from the ocean through precipitation onto land, plus how much sea level dropped because of La Nina, you close the hydrologic budget. So what happened in 2010, 2011 was the Earth system actually moved water from the ocean to the land. And because of the way that Australia is shaped, sort of like a continental basin, water does not rapidly flow out from the interior of Australia like it does in every other continent. So the signal persisted for the better part of a year or a year and a half, and then you see that sea level continued to rise again. So in conclusion, and I've talked a little more than the time was available, we in the space agencies, we in NASA, are making global measurements of many different quantities. We're combining those measurements through free and open data exchange to understand what is going on in the integrated Earth system. And from that understanding, we can deliver societal benefit. That's what we're doing as space agencies observing the Earth. Thanks very much.